break the record and finish early. All right. So today presenting some preliminary results did by one of my PhD students, Ji-Sang Lee, and he's just been conferred as a doctor. So we put the doctor before his name. Okay, so my topic is slightly different from most of the topics discussed in the workshop. I work on the pipelines, mainly the water pipelines, and my slides are gone. All right, it's back now. Okay. Um, so what we do is use the so-called hydraulic transient waves in pressurized water pipes to do something useful. So the hydraulic transient waves, if you're not familiar with, the basically pressure waves, dynamic pressure waves in the pipeline, and massive pressure waves can become an issue, to the safety and operation of the system. But if we control them, we can make use of it. All right, now this one doesn't work. Okay, working now. All right, see whether this, let's see whether this animation works or not. Right, so this just illustrate the concept, very simple, straightforward. So we have a side discharge, which is controlled. We can control the flow rate. And we have the so-called signal generator, which is basically induced by that discharge and the operation of the flow. Once we introduce a pressure wave by altering the discharge, the wave propagate along the pipe. And then if we have some discontinuities, we would get reflections from the system. So it's quite straightforward, similar to the sonar system, as you are probably more familiar with on the water object detection. Then by analyzing the reflections, we are able to tell, the defects in the system. So that is the principle. And one of the challenges we have in real systems, right, numerically it's all working fine, it's lab all working fine, but in the field, when we talk longer pipes and more complex conditions, we have this so-called signal dissipation and dispersion issue. So that means when you generate a wave, right, to ensure the resolution, you want to generate a sharp wave, right, from the time domain. So in the frequency domain, that means we have a relatively wide bandwidth. But as the wave propagate along the system, it experiences attenuation, but also the so-called dispersion. So dispersion means different components in the wave in terms of frequency, they travel at different time or different speed. So it's not just the size keeps reducing, but they actually further apart as they travel, different components, and then you have this so-called dispersion issue. And this definitely will affect the spatial resolution and the accuracy of our detection. So this is just some general illustration about the how that impact the reflections, from the defects in the system. In metallic pipes, it's less an issue, or relatively still, if you talk about longer distance, it can be an issue. But for plastic water pipes, it's really a significant issue. So, so what we did was to develop a technique to understand the wave dissipation and dispersion in plastic water pipes and see how we can deal with it, right? So at least we want to be able to calibrate that so we can take the dissipation dispersion into account when we're doing the anomaly detection. So that's the starting point, and but along the way we realized actually similar to the concept of using the pressure waves, which traditionally considered as a harmful, right, as something you want to remove and reduce as much as you can. Maybe we can use that signal dissipation dispersion as a tool for condition assessment. So rather than just to say, that's something we don't want and we want to remove or compensate, but we use it for something useful. So to prove that concept, that the signal dissipation dispersion, especially in plastic pipes, firstly can be calibrated, secondly can be used for condition assessment. We did some accelerated aging. So this is just to create different conditions, pipe sections with different conditions. So we put the pipes into relatively high concentration, relatively chlorinated water with relatively high concentration of the chlorine. And this just to accelerate the oxidation process of the pipes. Then after different wakes, right? We just pull out the sections at different wakes, which means they have different stages of aging or deterioration. And then we did the so-called material testing to quantify the material condition. Then after that, we did the so-called calibration of the frequency dependent wave speed and attenuation, which governs the signal dissipation and dispersion. So this is just a schematic of the system we used for the hydraulic testing. It's a single pipeline. In the middle, we have a so-called replaceable section. And then on this section, we can place pressure transducers. We use 2 pressure transducers to be able to tell the frequency dependent wave speed and attenuation. There is a particular method we developed to do that, and that method is useful because it helps to just focus on that particular section in between the 2 sensors. So in this case, in the lab, we only have one single pipe, which is a simple system. In reality, we know typically the pipes are in networks, and you would have complex reflections from other parts of your network. So the method we developed to calibrate the wave speed and attenuation is tolerant to those complex reflections from outside that bracket. So although this is not fully reflected in this particular case, because in the lab we just have a single pipe, but this method can be applied to sections in complex networks. Okay, then have a look at the results. From the material testing, we can tell the level of antioxidants. So that's what we can tell. Basically, in all the plastic pipes, we add in the so-called antioxidants to slow the aging process. But once the antioxidants being depleted, then you start to have the actual oxidation of the polymer chain. And once you have that process, the polymer chain will break. Then you lose the mechanical strength basically because the material actually changed physically. So the antioxidants is there to protect that. So we can say through the so-called material testing, we can see the level of antioxidants keeps reducing. So that OIT, that means, well, how many minutes until the remaining antioxidants being depleted. So basically we expose the samples with oxygen and heat, and we check, after how many minutes that, oxidants depleted, and then the actual oxidation to the polymer chain started. So as the OIT time reduces to almost 0, that means the antioxidants being depleted. So we can see after roughly 14 or 16 weeks of aging in our lab, the antioxidants being depleted. And then after that, we can't use that OIT to do the testing because the OIT only tells how much antioxidants left. Then we use another method called the carbon index to really measure the oxidation of the polymer chain. And as we can see with the time increases, that CI index increases as well. So this is basically what we want to say, and this helps to quantify the actual condition of the pipe. And then we had a look of the calibrated frequency dependent wave speed and attenuation. We can see the wave speed actually, we can see it keeps reducing, in general, in terms of the trend, when the oxidation wakes increases, right? And also you would notice if you look into more details, the for the first few weeks, I think up to say 12 weeks or so, the wave speed doesn't really change much. So that is sort of as expected because for the first, let's say, 14 weeks, the antioxidants still there, still something remaining at least. So we don't really have the changes in the polymer chains. We don't expect to see much deterioration in terms of mechanical properties. But after that, you say the change in the mechanical properties is reflected in that reduced frequency-dependent wave speed. Then similarly, if we look into that attenuation, which is again frequency dependent, we see a general trend that with the aging process, the attenuation will increase. So it's minus, but minus means more. In this case, means more attenuation. So this is just a snapshot shot of particular frequency, right? Because it's frequency dependent, right? So now it's just a zoom in to a particular frequency, which is 1500 hertz, and we can see on the top it shows the OIT and the CI, which represents the actual condition of the pipe. And then the bottom shows the wave speed and attenuation for that particular frequency, 1500 hertz. As we can see, up to say about 12 weeks, we don't really have much changes in both the wave speed and attenuation. But after that, we see a decreasing trend in the wave speed and increasing in the so-called absolute value of the attenuation. Okay, so in general, we have proved the concept that the friction-dependent wave speed and attenuation can be used as an indicator for condition assessment of plastic water pipes, and that is something useful because so far there's no cost-effective techniques for condition assessment of plastic pipes. Right, the only way is to cut a section from your field system, put into the lab, doing that OIT test or something else to tell, okay, that small sample is deteriorated or not, right? You can't see corrosion, right? You can't see wall thickness changes, you can't see anything. So our technique is potentially can be used in real systems without really cutting samples. We can keep the system working online, and we just do the testing, and we can tell whether your pipe is deteriorated or not. And from scientific perspective, before the depletion of the antioxidants, the mechanical properties is as original, and you don't really expect much changes in the wave speed and attenuation. But after the depletion, we start to see changes in the wave speed and attenuation, and the relationship is that the wave speed will decrease, for pretty much all frequencies, the wave speed will decrease. And for the attenuation, for all frequencies, attenuation will increase. Okay, so that's all. How's my timing? How I? Huh? Okay. Ooh.
So when you stand waves along the path, so will the internal condition of the path influence the wave frequency? Like if you feel the water or there's some additional stuff attached to the internal wall.
Yes. That's say for example, if you have a blockage, it will introduce reflections, and we can analyze the reflections to tell where that physical discontinuity is. And from the feature of the reflection, we can also tell whether it is a blockage or something else, like a leakage. So that is what we have been doing for a long time in the past. So what we're trying to do here is to understand the signal dissipation dispersion, because if it's a perfect system without any loss, right, and then any physical discontinuity will give you a reflection, and you just then focus on the reflection, you get everything you want, right? That's simple word, but the actual word is the real word is not like that. We have the strong signal dissipation dispersion, especially in plastic systems. When you send a wave after some distance, it's already very small. Even if you have some reflection, you may not be able to receive it because it's been dissipated. And even if you receive something, you probably can't tell what it is because it's been dispersed. So this is the new contribution we're trying to bring into the condition assessment of pipelines.
Thank you.